So you may have noticed on the program there are actually 4 talks on preference learning. So I am giving the first 2 talks today and tomorrow, I think, and then the next the last 2 talks will be by Eike Hüllermeier. I think there will not be too much overlap between our 2 talks. So I come from IRIT in Toulouse. So I start with a few examples of why we would want to learn preferences. Probably many of you are aware of that. So the first time I saw something about preference learning was it's in a paper by Thorsten Joachim, sorry, in 2002. So his idea was he was working on basically support vector machines, but he did a work on information retrieval. So the idea was you have a query, say on Google or anything like, and the system returns an ordered ranked list of documents, but this is not personalized because the ranking is made with Google scores, which do not take into account the user, the current user. So this, and it's well known that the ordering is essential. Yeah, you probably don't. Well, I do not often go to the second page when I have a Google query. And the question is, can this ordering be improved so that it fits better to the user's what can I say? So that it is more relevant for the user. So his idea was that there is a lot of data if you can observe the user when she interacts with the system. You can, for instance, memorize. You can write in a log file what the user has clicked on, and then it gives you some kind of preference, because you can say, well, the user preferred the things on which he or she clicked to the other ones. So it's very rough, but actually he showed in the paper that it did work. So it was a rather small experiment, but it did provide some improvement. So the thing is, what we are interested in with this data, the question is, can we learn, can we induce the user's preference, that is a relevance ordering on the answers to the query? So that's the first example. So if we have the model, if we can learn the model, then of course we will be able to rank the answers and to perform other queries if needed. So my the point here is that what I will be talking about is how can we induce one model of users' preferences in various settings. A second setting is a recommender system. Well, so this one is has been studied by Paolo Viapiani and can't remember the Pearl Poo and I can't remember who F is. But anyway, so yeah, you have you have an interactive system where there's there are a list of say of apartments that are available for rent or for sale, and you want to help the user to find the best one, the one that fits the best preferences. So at the start of the interaction, in fact, the user has very little well-defined preferences often, and so the elicitation process is going to help the user define her preferences, and of course the system also can build the model of the preferences of the user. So the interaction, so they use a particular type of interaction, which is example critiquing, I think, but that's not really the point here. So the good thing is that if we have if we have the model of the preferences, then of course we can try to find the optimal item according to the preferences. So here it's not the same end use. Here we want to find the optimal in the end item or good. And a third motivating example, that's something where we've been working on recently. You can imagine maybe you have already used say something like a car configurator or a computer configurator. Well, that's on some online shop. So here you don't have a fixed set of goods at the start. You are going to buy a car and you have to choose the color, the type of motor, the type of seat and everything. So there is a very large set of possible alternatives. And you want to guide the user so that to help her configure her preferred product, because there are so many possibilities that the users may quickly be overwhelmed by the number of possibilities. And to guide the user, you must know her preferences. So initially, the user's preferences are unknown. So, and in fact, when you buy a car, you don't buy a car every day or every other day. So you don't do that too often. So it's going to be difficult to rely on the user's preferences unless you want to elicit them. But that's a lengthy process. So instead of trying to elicit the user's preferences, another possibility is to say, well, most people have very similar preferences. And I've got a history of all the cars that I've sold until now. And this must show some preferences that are common to most users, to many users. And so if I take this sales history, can I induce one preference model that could fit the current user? Of course, when we do that in practice, there's not one preference that fits everybody usually, and it's with some experiments we see that the performances are improved if we do some clustering first, so that actually we cluster the users. Well, the sold cars, it's not the users, it's the cars that they have bought, but we can make some clustering to have several user preferences. But I'm not going to talk much about that. But anyway, so the idea is that I've got this sales history. I try to find some preference model that somehow explains that these cars have been sold most often and not other ones. And so if I got this model, then I can help the user suggest some options that most people take, so that the user doesn't have to correct everything or doesn't have to do all the configuration herself. Okay, so these are three motivating examples. And what is common in what I said, what was common for me in all these settings is that in the end, I want to learn a model of the user's preferences. It is not always the case, but in the end, whatever the settings, I'm interested in situations where I want to induce the model, the user preferences. Okay. Don't hesitate to interrupt me if there is something that I said is not clear, or if I say something wrong. Or so the general scheme that I have is that we have a decision maker. Somehow there is somewhere a target preference relation. So I suppose that it is a total ordering of all the a set of alternatives. And we have some data on the preferences, but we don't know this. And what we want is to induce a good approximation of this target ordering of the data. So total pre-order, it means it is transitive, it is reflexive, and it allows for it allows for indifference. And then if I've got this model, I will be able to to answer queries about I can compare 2 or more alternatives. I can order a subset of the alternatives, and I can find the optimal alternative. So of course, what I'm going to present is several models of preferences. There's several representations for such total pre-orders or for weaker forms of preferences. And depending on the model that we choose, some of these queries may be more or less difficult to answer. So this has to be taken into account when choosing a model. Okay. So I'm going to talk about 3 types of models. Generalized additive utilities, which is based on additive utilities, but with some more flexibility. Then I will talk about lexicographic models, and something which is a more logical type of model, where we have conditional preference statements. So a very logical way to express preferences. Okay. Just some notations. So I've got a set of alternatives, which is this big O. I've got, so I will use, well, there will be pre-orders on this set of alternatives. And so it essentially at the start, it is, I assume that the relation is reflexive, transitive. And we use normal notations, especially this one if an object is strictly preferred to another one. It's the same kind of curly symbol, but without the bar underneath it. Indifference, I write it like that. So maybe a bit confusing. I think in some papers you find it for incomparability, but I use that for incomparability. Okay, okay. And ideally, the strict part of the pre-order is a strict total order, but it is not always known, not always feasible. No, I have a finite set of features, attributes. I don't know how to call them. I call them variables in the talk, I think, all along. And so they describe the various alternatives are distinguished by the values for these variables. I assume that they all have a finite domain. I'm not talking about continuous domain at all. So I will write often with this we underline a variable to denote its domain or dx. And this notation, if I have an alternative O, this will simply denote the value of O for variable x, which will be useful in some formulas later. And N will be, so I will not talk too much about N today, but tomorrow I will talk more about complexity. And so N will be the number of variables. Okay. And we have, so I will often use letters like U, V, W for vectors of variables or sets of variables. Is the similar notations. Okay. So I start with additive utilities. So additive utilities, well, you've seen a lot of them already, I think, this morning. So I won't talk too much about it, but we've got a decomposition of, so we've got a value function, which can be decomposed with several value functions on all the variables. And we say that O is preferred to a prime if and only if the utility of O is greater than that of O prime. I guess this is something, well, anyway, the thing that I want to emphasize here is just that you can easily see that this ordering can be decomposed along these two directions, I guess. Is it clear to everybody why? It can be decomposed easily. So I have this ordering, and I want to find values so that it represents the same ordering. Yes. Essentially, the point is here is that whatever the main course, red wine is better than white wine. So you're going to put a big value here for red wine and smaller values for llama. This is going to, we're going to get the right the right. How does it work? Didn't I write the solution? No. But anyway, if I put 10 here and 0 here and say 2, 1, 0, it works. Okay. Okay. Oh yeah, okay, it is here. Okay. Now you can't not represent. You cannot use any additive utility to represent this. So maybe it's not that clear if I write it this way. But what is going to be important for me in the following is that if I want to check that, what I can do is I can write linear equations. Because if I have a decomposition like the previous one, then I will have, this is, say, a variable. I'm trying to find the values. So each of these things here is a variable. I must put a value for this. And so, for instance, the value for the first menu is the sum of the two values for the two variables for this. So the utility of land on red, and it must be strictly greater than the one for vegetable and red wine. And if I write all these equations, I think it is clear now that it has no solution. Why does it have no solution? I think here you have got something that says that lamb must be equal to vegetarian because they have the same wine. And I can't remember why. And this one here says that main must be greater than vegetarian. And there is another one. I think it's fairly simple. Lamb greater than vegetable. And here it must be equal. Yeah, of course, it's a contradiction. Okay. Am I right or not? Yes. Okay. So, so the point here is that additive utilities are not sufficient to represent fairly simple orderings. So we want to generalize that. And so we study generalized additive utility. So the extension is we take instead of summing over variables, we sum over subsets of variables. So we add some flexibility here. There is a set of sub-utilities here. So it could be any subset of the variables. I can take any collection of subsets of the sets of variables. And I define a utility, a sub-utility on each of these sets. So it's defined on the domain of each of the sub-utilities. And I sum them. And I take the same definition as before. So with this, we've got something which is a lot more expressive. Something that is not, maybe not clear. These U's define a hypergraph over the set of variables. You've got, if you think in terms of graphs, you've got all the variables, and you have an hyperarc is going to be something that is going to contain each U is defining a hypergraph. Okay, I mentioned I come back later. I will use that a little bit later. I will refer to that a little bit later. We can represent every total preorder with that. That's quite clear because we could take the biggest we can just define a utility that orders everything. We can just set this, well, we can consider a single click U, which is the set of all the variables, and we can just define our utility so that on this set, so that everything is representable. Is that clear? Not too sure. So it's very expressive, probably too expressive for machine learning. So it's called a graphical model because they use defined hypergraph. And this kind of things that share many computational properties with, for instance, Bayesian networks. So I'm not going to talk about that. But the point is that the algorithms, some of the algorithms that are used to make some inference in Bayesian networks are very similar or the same as the kind of algorithms that you can use to make some inference with generalized additive utility. So of course, it is more difficult than with singly additive utilities. So in particular, comparing two alternatives is easy. You just have to compute the value of the two alternatives, so it's very easy. You can order a set of alternatives in polynomial time. So if I come back to the information retrieval example, I've got my list of documents that the system has retrieved. And if I want to rank them, I just have to compute the value of each of them. And then well, it's actually, it's just a sorting algorithm. So it can be, it's not even quadratic. It's in n log n. So I can rank them. But finding the optimal alternative is hard. So this is something very general. And with Bayesian networks, there are queries where a lot of queries are NP hard or NP complete. And here, finding the optimal alternative is NP hard. And something that is important here. So you have this hypergraph. And there is a parameter of the hypergraph that measures somehow the biggest calculation that have to be made, which is called the tree width of the hypergraph. And the smaller this tree width is, the faster the computations will be. Okay, but so there are a lot of these are very well-known facts, and you've got, for instance, a lot of algorithms and complexity results in this sort of survey paper here. By Martin Cooper, Simon de Givry, and Thomas Schiex. I've done a lot about that. It's not explicitly about generalized additive utilities. It's more about the family of graphical models, where they give a lot of reasons. Anyway, so what is interesting here is that if what I want to remember is that if I have to choose a model, I must keep that in mind. Before I try to decide to learn something, I must keep in mind that some queries are hard and some queries are easy, depending on the model that we are going to learn. Okay. So now this question of queries is you have got your utility, you want to compute to answer some queries. You've got the queries, the complexities that are here. What is more important? So it's not obvious at the start, but there are many ways to represent the same ordering with this type of decomposition, and this is something that is going to be important for machine learning. So here I have a set of 4 variables. So we have 3 utilities, one over the 2 variables x1, x2. They are all binary variables, huh? x1, x3, and x1, x4. Right, okay, so you've got a table here which gives for each combination of values for the 3 clicks, you've got the value. Now, in fact, I can take something fairly different and I can get exactly the same ordering. So if you look at that, what is it going to say? Well, the first one is not surprising, it's the same. The second one is somehow more surprising. Why is it surprising, the second one? Okay, this one, you've got roughly you've got the same. It's not exactly the same order actually, but this one is better. But there is something here which shows that there is something very strange with these utilities. And the thing is, here I have x1, x3, here x1, x4, and here the ordering is over x2, x3, x4. So this is something quite strange. You've got two representations, but they don't have the same clicks, but they don't have, you cannot even say that one is more refined than the other one. They really have completely different supports. So here, well, I'm not going, well, yeah. The question is, can I find when you want to do some machine learning, you know that you want to learn something that is simple in general. So the question will be, can I define something which is simple with this sort of decomposition? I have a good way to define something which is somehow the smallest object, the smallest model that I can choose. So if we want to do that, we can define a refinement. So a refinement, essentially, you've got two decompositions, and one is a refinement of the others. So G is a refinement of G prime. So you can see they have these subutilities. They don't have the same sets of variables. So of course, one is a refinement of the other one if they define the same ordering. So if the ordering associated to G is the same as the ordering associated to G prime. And also, for every subutility here, there is another one here which is smaller. I wonder if there is not a mistake here. Let me check. For one, a bit dubious. Way, is it the right ordering? Refine, I thought it would be that the clicks are smaller. And here, yeah, that's it. Yeah, that's it. Here, I have something smaller than the other one. Okay. So anyway, with this notion of refinement, the thing is that these two, because we could wonder, maybe there is something, if I come back to this example here, we can wonder, maybe there is something which is somehow smaller as a representation, at which is going to get the same ordering, and which in fact will be a sort of better than these two. And what can be proved? It actually none of these two can be refined. So these two are somehow two most simple utilities, and they are widely different. So this is going to be a problem for, well, this may be a problem for machine learning. Not a big problem, but it's a problem. So now I come back. So now I go to learning. So I have I come back to this general learning setting. I have my pre-order, which is this one with this small curly symbol on the top. And here I consider the settings of batch passive learning. So I have passive learning. I have a set of pairs that they have all arrived in the batch. I can't do any interaction. So this is my sample D, and I want to learn a representation of total pre-order that is as close as possible to the target one. Okay. So the question is, so maybe here, I don't know. I assume that everybody here knows a little bit about machine learning, because so everybody knows what a loss function is. Yeah, I thought I could assume that easily. Tell me if anybody doesn't know what a loss function is, but I think the case. So what the loss function that we can use here is the number. So I've got these two things here. I must somehow measure how this one is going to fit this one. And the loss function, a first loss function that is useful is the number of pairs of alternatives like this one, which are wrongly ordered. So this is a well-known distance between orders, between total orders, and this is called the Kendall-Tau distance. Okay. So my point will be try to minimize this noise when I try to learn something. Now I've got this. I know that generalized additive utilities can represent every total pre-order. So I need to add something because otherwise I'm not going to learn anything. So one efficient thing to do is to put a bound on the size of the clicks. I am going, so what, if you've got singly additive utilities, you've got a bound of 1 on the size of the utilities. We want to do something more general than that, but if we go to something too general, then it is going to be difficult to learn something. So we're just going to say there is a bound on the size of the clicks, and we are going to try to learn that. So I call it the degree of the additive utility. I think it's been called recently with a different word in a very recent work on general additive utilities. But anyway, so the degree of my model is going to be the maximum of the size of all the clicks that I have in my decomposition. Okay, so it's just the maximal of the cardinality of the U's that appear in my decomposition. Okay. So now I set some k, some parameter k, and then I want to induce a decomposition which has a degree which is less than k. So my decomposition, well, if I want to, I don't know anything at the start. So my decomposition will have this form. I'm sure that this is, if I can find one, it can be written in this way. So it's a big space. So what does it mean? I take all the subsets, all the parts of the set of variables that have a size less than k. And my my algorithm, my learning algorithm, can explore this entire very big set of models. So now, how can I explore that? The good thing with this approach is that, in fact, there is a polynomial time algorithm to do that, which is quite understandable. So you remember on the slide, a few slides before, yeah, there were some, I had an ordering, and I said, well, we can write the constraints on the utilities, and there are linear inequalities or equalities. And if I fit that, then I've got the same ordering. If I can find the values for my utilities that obey these inequalities, then I've got something that represents the right ordering. Well, I do the same here. I take every pair in my sample here. And I say that the sum of all these utilities applied to the object to the alternative O, so the value of O for every of these U, must be greater than, since O must be greater than O prime, this is the meaning of something being in my sample, greater than the same thing on the right-hand side. And because I have a strictly greater than here, I must add a parameter, which is a small step. So actually, you say, well, I could put a strictly greater than here. Why am I not doing that? There is a very obvious reason, is that I'm going to solve these inequalities, and then I'm going to optimize something, and this is just simple linear programming. So I can solve that with any polynomial time algorithm for solving linear inequality, solving linear programs. So this is actually a linear program. So that's why I don't put this strictly superior here, but I put a step. Okay. So an example. So here I've got two alternatives, x1, x2, x3 bar, x1 bar, x2, x3. I set k equals 2. I put a sigma, 0.1. This is not important, since in the end, it's not the values of the utilities that are interesting for me. It is only the ordering that they induce. And so here, the decomposition, I don't know better than putting all the possible decompositions. So there may be a utility with the variable x1. So I must have the variable. So this is a variable of my linear program, the one that I'm going to try to solve. I must find a value for ux1 and another one for ux1 bar. So these are the two possible values for the first utility on x1. And I must find the value for ux2. So here it is the same actually. So they are going to be to disappear if I write the system correctly. Here I've got ux3 bar on ux3 and so on. And so I've got here all the values for the single utilities, for those which have a single variable. But I must also add variables for all the utilities that pair on two variables. So these are the ux1, x2, ux1, x3 bar, because here we've got x1 and x3 bar. And to the opposite, and on the contrary, here on the bottom line, for O prime, we've got x1 bar, which is here, and x3. Okay. Okay. So clear? I just have I've got all my examples, and I can solve this linear system of equations, and I will find something that fits the examples. Okay. If, of course, what can happen is, of course, that the examples are contradictory. If there is something wrong in the data, if there is some noisy data, this is not going to work. This is going to be this system of inequalities will not have any solution. But okay, I just come back to that in a few months. So the question is, how many inequations that is will there be, and how many variables? It's going to be a big system. If I take k equals 2, it's okay. If I take k equals 3, 4, okay, it's going to grow. Okay. Yeah. If one of the examples was not strictly, but because in some settings we may have that the examples mean something slightly different, that O is at least as good as O prime, then of course I don't have to put the sigma here. It doesn't change much. So I solve this system. I've got one inequality for every element of my sample. Okay. So now the question is, how many variables do I have? Well, I've got a lot of variables, but not that much. Because, so maybe I should come back to that. If I just look at that, assume that we have binary variables. How many variables altogether do we have? So I should have done that differently. Actually, so this number here is the number of subutilities. Okay. So now, if I have what is the cardinality of a subutility? Here I'm summing. So for I equals 0, it means the subutility with cardinality 0, it's a constant. Here with k, it means the biggest subutility with cardinality k. And how many variables are there? How many values do I need to compute for every subutility? It is going to be, so suppose that all the variables are binary. I'm going to do that. It's simpler, but I've got 2 to the power of I values. Okay, there are 2 to the I possible combinations of values for each subutility, which has a cardinality I. So here, altogether, I would have this sum with a 2 to the I. This would be the number of subutilities. So it's a big number. But if I come back, I think we can see that in that example. If you look at that, here, only a few of the variables appear. Do they appear all of them here? No. So for example, for x1, x2, there are only 2 combinations that appear in this inequation. For x1, well, these ones are so small that they almost, no, even here, the ux2 bar does not appear. Here, we have ux1, x2, ux1 bar, x2, but the other 2 combinations do not appear. And in fact, it turns out that if D is not exponentially large, then the number of variables that I need, instead of having this 2 to the I number here, I have something which is much nicer, which is a bound, which is the cardinality of the, because each of the inequalities can only introduce as many as that variables. Actually, there is a mistake. Yeah, sorry. Just notice that, but since I will be interested in asymptotic complexity, it should be 2 here because we have got the variables on the left and the variables on the right. And for each utility, each inequation can introduce 1 variable on the left and one on the right. So actually here it should be a 2. But it is not too big. So anyway, the thing is, I've got this number, which is, well, it's not too small, but it's not too big either. It is a fairly decent bound. And now I'm going to, it's not cheating, but what I say is that if I fix k, then it's polynomial in k. If I fix k, then this number is polynomial because the exponent appears with this sum here. So if k is fixed, then it's going to be okay. Okay. Okay, so I've got a system of this number of inequalities, and the number of variables is going to be polynomial in n. So that's fairly okay. You've got, I come back to the case where I've got noisy data. So there may be some of the example in D may disagree. So I've got to handle that. So how can I do that? I just have to add the slack variables. So which makes that this could actually take a negative, negative or positive value. I think it's positive. So this could take, if I cannot find something which fits all if I don't have a solution with this, well, if I add these variables, then I may have a solution because these may take the values that are enough to make something bigger than something else. And of course, because I want to minimize the loss, because the sum of these things actually is going to be something which somehow represents the loss. It's not exactly the loss. It's not exactly the number because these variables are not going to be 1 or 0, but it's something that that actually is going to be to represent somehow the loss. And I want to minimize the loss, and so I'm going to minimize that. Every time this slack variable takes a non-zero value, it means I needed to do that to otherwise my utility would contradict this this inequality, would contradict this exam. So every time this is a non-zero value, when I have solved the system, it means I have something that that is opposite to the sample that is here. And so I want to minimize these things. They are going to represent the loss. Okay, so this is something that I know how to do. I've got my I've got a good solver for linear programming. I can do that. Okay. Now, for some regularization, the thing is with this we have got absolutely nothing that that is going to say that we want something rather small. We've got this bound on k, so actually my solution could be something which has which can be refined in terms of what I've shown before. I could have the solver. I don't have any clue how the solver is going to work. And it could give me something which has a much bigger representation, that is much bigger clicks than actually needed. Okay, it's not going. The clicks are not going to be to have a size greater than k, but still it could be up to k. So if I don't want to avoid that, I had to do I had to do some regularization. So I can. There are two things easy to do. There are some other things that I could do. I can minimize the sum of the variables. So it's on top of minimizing the loss. I will add that to my objective, something. So if I add the sum of the variables, the idea is that I will try to minimize the number of non-zero parameters. So that means my utilities will have a maximum of zeros, which is good for representation because when you represent that, you can say the default value is 0, and when I don't give the utility for a combination of values, then it means it is 0. So this is going to minimize the size of the representation, and of course, it can be hoped that the big sub-utilities, the one that have a lot of variables, this one have a lot of parameters. So if I try to minimize this number of non-zero parameters, then these utilities will disappear. Only the smaller ones will remain. So that's one possibility. And another one is to minimize the degree of the model. So I have my fixed k, and I can say, well, let me try to minimize the maximum degree of the utilities that are used. So I don't know how familiar you are with combinatorial optimization, but minimizing a maximum like that, it is you need to do some. It becomes a mixed integral linear program. That is, you have some Boolean variables to do that. Say, if I will put some Boolean variables, I'm not going to put the entire program here. It's a bit a big one, but I'm going to put some Boolean variables that say there is a utility of size k-1, for instance, and I'm going to try to minimize these variables. So that's not very efficient. Mixed integral linear programming is hard. Solving a mixed integral, well, solving a linear program with Boolean variables is a hard problem. It's NP difficult. So it is actually more efficient to try. I set some k, and if it works, I can try with k-1, and again, and at every iteration, I can try to reduce my k until there is no, I can't solve anymore with a satisfactory loss. Okay. I think this is it. Yeah.
How about the regulation of the steps? The sigma. The step.
Yeah, it doesn't matter. You can take anything because it's not going to. If I okay, if I take this I take this for instance. Where is this? No, it was this one. Okay, I take this. If I take a step of 1, basically I can find a utility where this is going to be 0, this 1, 2, 2, 2, and 3. If I take 0.1, it's just going to squeeze the thing, but the steps will be the same in the end. So the sigma is not really important here. I guess you have to choose a value which is not too big or not too small, so that not to have too many overflows, or but any value. It's not going to change the ordering anyway that you get in the end. So that is the most important thing. Because since we try to minimize the steps, in the end will be the sigma.
The steps can affect the k. If the step is large enough, then k will be can be 1.
No. It doesn't. As I said, if how can I say that? If I take
sigma is large enough, then all this can be easily transferred.
If sigma is large enough, no. Well, here I've got this strictly superior, so I would put superior or equal to, and with a sigma here when I translate that. So actually it is exactly the same thing, because when I am going to start my solver and I'm going to try to solve the sum of the utilities, well, it works with that. Huh? It works with I must minimize the sum of the variables. So the sigma is going to be chosen as the utilities are going to be chosen in the end by the solver as small as possible, so that the sigma is not violated. But because of it is not a matter of k. It has nothing to do with k. I can take a given sigma, and if I take half of that, I'm going to have exactly the same solution, because all the inequations will have the same sigma. And it's not a parameter, it is fixed. So it's like a constant that I put on all the inequations. So yeah.
How large can k be? You said it's a constant, so it's different if you have 1 million, k equals to 1 million than 100, for example.
No, but if I assume I've got say 20 variables, if I take k equals 20, it's not going to be manageable. Or even 10 is going to be too big. K has to be fairly.
So there will be some constraint on k, on the value of k.
From a practical point of view, yes. Depends on how much time you have and how much computing power you have.
So that the problem can be tractable.
Yeah.
And also, can you solve some relaxation of the MILP problem instead of doing this iterative k thing?
But it's not going to give you the right values for the Boolean variables. So
it's just an approximation, so you can get something out of it.
Maybe I don't know. I've not tried that, but yeah, I couldn't say. I should be experimented maybe, but I don't know. Yeah. But actually, if you try to relax the problem, isn't that the same as you solve another system which has the same size? But you're going to have 3 or 4 iterations. Because if you take a small k, say you start with k equals 10, which is already a lot, you're going to be fairly quickly at small values of k. So
yes, but maybe the relaxation would work better.
Yeah, maybe.
If you find some way to how to get your
maybe. Okay, so now I switch to I've got what, half an hour? Is that correct? All right. Okay. So I'm sorry. Actually, I didn't know. I don't know why. I thought I would be talking in French, and I started to translate some of the slides. I hope I didn't have time to translate everything in French this morning, in English this morning. So there will be. So do not hesitate to interrupt me if there is anything in French that you don't understand. For those who if you don't understand French, I'm really sorry, but I did not realize that. So now I'm talking about lexicographic models. So this is another type of model, which is completely different from the additive utility, generalized additive utilities that we've just seen, which has very interesting properties, as you will see. And one bad property. So lexicographic, you all know how dictionary works, or telephone book. So it's you've got this sort of, so this is the basic model is just a lexicographic ordering. So you've got an importance ordering, which I often write with this triangle to the right. So here, wine is more important than dessert and is more important than main course. So this is my choosing a menu at the restaurants, for instance. Actually, I would usually put dessert in front of wine, but so I assume that that I have this So this is an importance ordering. This variable is more important. This is for me the one that is going to decide everything else. And then for each of the variables, I have a local ordering of its possible values. Here, it's not a very big restaurant, so there's not much choice. Well, it's the only, well, it's already good. You have 2 vegetarian choices for the main course, so it's already a big restaurant. But there are not that many, not that many menus here. Is it okay? You understand how it works, huh? I guess. I'm not sure my notations are clear, but otherwise, so here it means, for example, that well, I'm not going to give an example. It's too easy. So it's very, the expressiveness is very limited with that. Okay, there are many orderings that you cannot express with that. It is even less expressive than generalized additive utilities, or even than additive utilities, I think. So what a model that on which is a bit richer than that. We put some, it's the same kind of model. You have a root, and this is going to be the most important variable here. And then the ordering may depend on the value that you choose for the most important variable. So you can, it means that the ordering of the menus that have, well, the menus of the alternatives that have the value big T equals T is different from the ordering of the alternatives that have this value here. So I'm going to have something which is a lot more expressive. And it is represented with this tree. In terms of, you'll see that in terms of machine learning, it's somehow, and not only for machine learning, it somehow resembles decision trees. Right? When you have got the same kind of representation, even if it's not to represent a decision, but it is to represent an ordering. So I've got these local orderings here are let's call them the conditional preference tables at every node. If I've got a node n, I've got this conditional preference table. My table, each table must put a strict ordering on the values. If I put, I have to say that one of the, here they are binary variables, I have to say that one of the 2 values is strictly better than the other one. I can put some condition here for the ordering. So this table here says, for instance, that if D is the case, because in this branch, I can only have T bar. But if D is the case, I will have that C bar is preferred to C. And if D bar is the case, then C is greater than C bar. Okay, so I've got this flexibility to put some condition on the tables. Of course, this here I've done this. It was interesting to do that because here there is only one child, and because there is only one child, it means that in terms of importance, having D or D bar doesn't change the order. It's normal because anyway there is only one variable left. So here it would not have any meaning to put one branch with D and one branch with D bar, because okay. So every node has either no child, it is a leaf, or one child like these ones, or it can have as many children as there are values, like here there are binary variables and we have 2 children. So is it clear, if I give you a few seconds, why this holds, that CDT is preferred to C bar DT bar? So they both have, well, this one is very simple. I go to the root and I compare them because T is the variable. I compare them with their values for T. So this one that has T, it's a lexicographic principle. So T is the most important variables, and this one has the preferred value, and this one has the less preferred value. Okay. What is the most preferred alternative? So you just have to go down the tree on the left hand, on the left branch. So you can take T here. Here it says that it is C bar and D. So it is a T, C bar and D. Okay. So these models, that shows that you can guess that when with what I've done, it's very easy to compare 2 alternatives. It is very easy to find the optimal alternative. I just have to go down one branch well, so there is it actually to such a tree corresponds exactly one ordering, which has this top alternative, which we have just seen, and you've got all these inequalities. Okay. Okay, it's clear how it works, how I can order everything. So CPTN, just some notation. CPTN is the conditional preference table. Instant N is the set of attributes. So if I take this node, for example, the variables that are instantiated at that node, there is only T here, because this one, there is a single branch, so I don't know which value D has when I come here. Instantiated means that some variable already has a value. When I am at this node, T already has a value. So the set of instantiated variables is just T if I take this node here. And when I am the root, of course, it is empty. So a tree like that defines linear ordering, which is total, strict. Okay, skip that. Now, if I take this, can take it for granted. There is no tree like the one I've just described that can represent this ordering. And what we need to do to represent it is already quite expressive, but there are things that I cannot represent with that. And what I need to do is what I did with utilities. I need to be able to put some set of variables at the node. So if I come back to that, for instance, if I had an ordering that I cannot represent with it, I could group 2 variables at the same node, and I will get some more expressivity. I would put an ordering on all the combinations of values for CD, for instance. And this is going to add flexibility to my model. Essentially, this model is very restrictive because it means whatever you take with conditionality or not, it doesn't matter. It means that some variables are more important than others. And this is not always the case. You may have situations where actually you don't have really one variable which is more important than another one. So if you want to define an ordering on the values of these two variables, you have to actually define the table, define the ordering on all the possible combinations of values. So if I take this k, then I greatly augment the expressivity. Actually, what I could do, I could have just one node, the root, which has all the variables, and then I just can represent every possible ordering at the root. So this is, of course, too expressive in a sense, but we can do that. So in an actual machine learning context, we'll have to put a bound on k. We have to learn lexicographic preferences with a bound on k. Okay. So what is good with these trees? Comparing two alternatives is easy. Just go down the tree as long as they are equal. Ordering a set of alternatives, well, you just have to compare your alternative, you order them, so it's easy. And finding the optimal one, you just go down the left branch, and it is easy. So in terms of queries, the queries that I've mentioned up to now, these are very interesting. Everything is easy with these models. They are different from additive utilities, and they have only polynomial time queries, whereas this one for additive utilities, generalized additive utilities, is hard. So now, just hope I have time to do something. I have to talk about the rank. So you know this tree is defines a total ordering of all the outcomes. So I can rank them. And I can compute easily. This is what I'm going to show now. I can easily compute the rank of any alternative. And this is going to be important because for the machine learning setting that I'm going to talk about after that. So I take an example here, which is the alternative WC1P. And I assume that I want to compute its rank. So one way to do that would be I compute the entire ordering, and then I just count the ones that are better than WC1P. But I can do that directly. Essentially, WC1P is somewhere in my tree, and its rank is essentially the number of alternatives that are to its left in the tree, because these are the ones that are better. So if I take this one, for instance, it has value W for the first variable. So it means that this WC1P is going to be less preferred than all the ones that are in that branch. And how many alternatives do I have in that branch? It's fairly easy to count because I know the size of the domains of all the nodes that are below it. So here it is 6. Actually, I can find them here. It is 3 times 2 because C has 3 values and P has 2 values. So in that branch, you have 6 alternatives that go down that branch, and they are ordered here. So W, the rank of W is at least 6, at least 7, in fact. Okay. So now I have WC1P. So I have P here. So I can see that here there is the same kind of consideration, which says how many alternatives do I have when I'm here that have P bar, because all these ones are better than WC1P since P bar is better than P. So how many alternatives do I have that have P bar? Well, I just have to count how many values I have for C. There are 3. Okay. So I got 3 of them. So in the end, this means that and I've got C1, and here C1 is the second value. So there is one alternative which is better. So if I go down the tree on the path that corresponds to WC1P, WP, and C1, I can see that at every node I can gather the number of alternatives that are worse, that are better. And here it means 6 plus 3 plus 1. I've got 6 here, 3 better here, and finally 1 better here. And I add 1 because the ranks start at 1. So the point is that I can easily compute the rank of any alternative. And I've got this formula. So I'm not going to too much into the details, but the important thing here is that if I give you a tree, phi, an alternative O, then I can compute the rank just by summing some things along all the nodes of the tree. So I can decompose my rank, my formula in this way. I have this interesting formulation of the computation of the rank. So here, this indicator function is just to say that we don't consider nodes if if they are not on the path. So this is going to be 0 if I'm not on the right path for the alternative. Okay, so I've got this nice decompose way of decomposing my value. Sorry, no, my values, and here, just think. Here, what this small r is, it means the local rank at the node. Okay, if I have the value W, for instance, its local rank was 2 because W bar was better, and the rank at the root was 2, and I had 1 because rank start at 0, and I just want to count the alternatives. So there is something a bit funny here. I have a 1 plus to make it a rank, and here I have a -1 because I don't want a rank, but it works well. Okay, so now to the learning part of it. I've got a target and non-total pre-order still. So now I am in the context of this car configuration web page. So I've got a history, a sales history. So I've got a list of items that people have bought in the past. And I can assume that these things are items that people liked. Otherwise, they would not have bought them. Maybe it was not their best alternative, but anyway, I assume that that they are there because people like them. And actually, some of these. So it is. It's wrong here to say that it is a set. It is a multi-set. Several items will probably appear several times. There are a lot of people who have exactly the same car when you look in the. Well, no, it's not because they prefer it. Maybe the commercial people at the company who try to make them buy such cars. But anyway, you have a multi-set of pairs of sold items. You've got a lot of them, and what we can expect from this set is that all these if all these people who have bought cars, because we don't buy a car every day, if all those who have bought these cars have similar preferences, then for all these let's say there is one preference which guides all this process, one preference tree or anything else, but here it will be preference tree. Then all these items have low ranks in that preference. They are the most preferred somehow in that preference, and so it means they have a low ranks with respect to this total pre-order that I don't know, but that I would like to induce. So now how can I do that? It is here. I want to induce something that is a pre-order that is as close as possible as that, just by looking at these things. So what I'm going to do, so I introduce here, because I got to talk about the loss, some more detail. So I suppose that there is a probability distribution P over the set of possible cars or whatever. And this probability is linked to this. I assume that this probability is decreasing when the rank increases. The most preferred items have the higher probability to appear in the multi-set, in the sold items. That's quite normal, because if you can imagine a process that generates this sample D, of course, we can assume that the more preferred something is, the more likely it is that somebody is going to end up with that, with her configuration process. So we assume that its probability is decreasing when the rank increases. And then what we are going to look for the loss function, we want a loss function that increases the rank expectation. So what I want to do is a kind of Spearman rank correlation. So Spearman rank correlation, it is another measure of orderings, but Eike will, I think, talk in more detail about Kendall-2 and Spearman rank on Thursday, I think. But Spearman rank, well, you probably know that, but it measures how close, well, it is a way to measure how two ordering are close to one another by just comparing the ranks of the items. So the thing here is that with our learning algorithm, we want to be precise on the things that are preferred. So in our loss function, we are going to consider an expectation which is in accordance with this P here, which is, this means that the items that have higher probability of appearance, well, the mistake on the ranks of the things that are likely to appear with a high rank here are going to be considered better, are going to have a more importance on the computation of the loss. So this is why I need to introduce this P here. So my loss function with for an ordering, the one that I'm going to compute with respect to the target one is just the difference in the ranks, in the rank correlation, but somehow it is weighted with the probability that some things appear in the target model. And okay. So I can do that. So now I want to compute a tree which has a minimal rank expectation. So I want to minimize this. I want to minimize this loss. And so because this is a constant, it doesn't depend on the model that I compute. So I just want to minimize this term here. I want to find something which has a minimal rank expectation. So of course, I don't know P, but that doesn't matter. I have some estimate of the probability because I've got this history, which somehow gives me the frequencies of the items in this history, gives me a good approximation of this P here. So I'm going to compute the LP tree with minimal mean rank expectation. So if I come back to this formula, now instead of a P here, I've got the expectation with respect to my sales history, to the number of items. So here, actually the P here is the frequency of appearance of some things. And I take the same formula, but I do it not with P, but with the frequency of occurrence of the things in the history. So when you learn graphical models, and this is not really a graphical models in the same sense as I gave earlier, but one thing which is often the case, you have two different things. It's the same with Bayesian networks, for instance. You have to learn the structure. This is often a hard problem. And then you have to learn the local tables, and in general, it is easy. Here, if I have decided if I am at a node and I have got the variable that goes there, then I only have to order the values very easily with the frequency of occurrence, with the frequency with which they occur in the sample. So now, so this is going to be somehow, this is going to be the best local expectation that I get at the node if I order well the values of the variable that is at that node. So how do I do now? The first thing is if I want to learn an LP tree, I showed the first one, a linear LP tree with one variable at each node. Well, this is very easy. I can define this score, and you can easily to check that actually if I order the variables according to this score, then I will have the tree that has the minimum expected rank. Okay, so learning a linear LP tree with univariate nodes, just one variable at every node, is easy. And now if I want still a linear LP tree, but if I want to allow several variables at every node, Then I can use the same score, but it doesn't. I have to enumerate all the partitions of my set of variables, and for every of these partition, compute the tree that has the minimal value, the minimal expectation. And so it's not as easy. I must enumerate the partitions. And if I want to know a tree that is not linear, well, yeah, I'm just going to stop in a few minutes. If I don't want something linear, I will put a bound on the number of leaves, and I will use a greedy top-down generation, a little bit like I do with decision trees. And of course, I've got some heuristics to guide the choice of the set of variables. So my heuristics will still take into account the score that I just mentioned. But I also have to check if I take a set of variables. Let's show that on an example here. Where do I have a tree? Okay, here. If I, for instance, suppose that I want to learn this tree. If I take these two variables for the root, okay, I can quickly discover that actually it is better to take W alone, that W alone works as well. If I got some good measure of how well something fits to my example, then I should see that I can take W alone. And taking W alone is better because it makes a smaller tree. It makes the tree more precise. So this is where I was. Oh yeah, I've been too far. Okay. Okay, so I've just my heuristic is going to take these two things into account. Okay. So I think I'll stop here for the lexicographic. No, just one word about something else. So here I had this settings of sales history, and I want to find something. So it's called we called it unsupervised because we didn't have any label on the data, just this list of sold items. Most of the work on that I know of on machine learning on preference learning has been done. Well, many works have been done with this kind of models on a setting where you have pairwise comparison at the start. And there have been a lot of works that show it's fairly easy to have, instead of having this history, to have a set of pairs at the start and to induce a learned representation of a total pre-order. And then the loss function, it's going again the Kendall-Tau distance, but it's really the same kind of pre-simple as with learning decision trees here. Okay. Okay, so I'm not going to explain that too much because it's in a sense it's not very original with respect to other things that are well known. Okay, so I think I'll stop here for this part. Thank you for listening to me.